Hello guys, it's JohnnyTime and welcome to another smart contract hacking guide and to the Damn Vulnerable DeFi version 4 solutions series. Today we're going to solve the 6th challenge, which is Selfie, and we're going to learn about governance attacks and DAO exploit. It's going to be super interesting and exciting, so without further ado, let's get started. Challenge 6, Selfie with Foundry solution. A new lending pool has launched. It's now offering flash loans of DVD tokens. Awesome. It even includes a fancy governance mechanism to control it. What could go wrong, right? You start with no DVD tokens at all in balance, and the pool has 1.5 million tokens at risk. Rescue all the funds from the pool and deposit them into the designated recovery account. So we have a pool with flash loans and governance, and we need to exploit it. Let's get into it. We'll start by reviewing the Selfie pool contract. We see that it uses some open Zeppelin contracts like ERC20, Reentry GAD, flash loan lender and borrower interfaces. So it's a classic flash loan pool like the previous exercises that we had. We have the token contract and the governance contract defined in the state of the pool contract. We have some predefined errors over here. We have a modifier, only governance. As you can see, I leave some audit comments through the code when I solve the challenges like I'm doing when I'm doing smart contract audits. This is awesome. I recommend you to do it the same. I leave this audit info comment that only the governance address that is set in the constructor can bypass this modifier. We can see that in the constructor, we pass the token and governance and set it in the state. We have other functions here like max flash loan. I already have audit info comment, so I don't need to read the function again. In this info, I just explain the function to myself. Max flash loan is the balance of the token in the pool, so anyone can just take all the liquidity from the pool in a flash loan. Here I have another audit comment that the flash loan fee is always 0 for all tokens, so we can take flash loans without fee for free from this pool. And this is the flash loan function. So we pass receiver, token, amount, and data. It's non-reentrant, and it checks that we can only borrow this token or it will revert with unsupported currency. It transfers the tokens to the receiver. It calls the callback function and makes sure that we return from this callback function. The receiver needs to implement this flash loan callback function and return this callback success hash, or we revert with callback failed. And we try to transfer from the tokens from the receiver of the flash loan back to the pool, to the contract. And if the receiver did not approve the tokens, it means that the transfer form is going to fail and we will revert with repay failed. And eventually we return true. So everything looks legit, safe, and secure in this function. We don't have reentry, we have non-reentrant modifier. We can only borrow the token. We have a callback and we make sure that we got the tokens back. We just get all the amount back. So nothing to hack here, actually. Nothing too interesting for hackers to break. It's very simple, straightforward functionality. Now we have another emergency exit function here, and I left here some comments. Interesting way to drain the pool. Can we be governance? Okay, so I'm asking myself question while reading the code. This is what I'm doing during smart contract audits, and this is my tip for you. And I can see that this function receives a parameter receiver and only the governance can call it. We already know what this only governance token stands for. And then it takes all the balance of this pool and just transfer it to this receiver with an emergency exit, So it's some kind of like emergency mechanism that in case something goes wrong, the governance can pass a proposal and just get all the funds from the pool. So our goal to drain the pool is to become somehow the governance, but how do we become the governance? Because this modifier makes sure that the message sender is this governance address that was defined here in the constructor. So it leads us to reading the next contracts, the governance. So we have the interface of the governance. I know that at this point, you might think you lack some technical knowledge to understand all of this with ease. That's exactly why I created this smart contract hacking course. Instead of piecing together scattered resources, you will follow a structured learning path together with hands-on exercises that simulate real-life attacks. When you get stuck, our Discord community with security researchers and fellow students is there to help. And once you've mastered everything, you will earn an official certification to validate your skills. Transform from watching tutorials to actually understanding smart contract security. Visit our website to start your journey today. So we have the interface of the governance. First, we have a struct of governance action, value, proposed at, executed at, target, and data. We have some errors defined over here and the functions that will be implemented in the next contract, simple governance.solve, that we're going to read. Let's take a look at this contract. It uses the Damn Valuable Votes contract, which is another contract that is an ERC20 votes. So it's kind of token with snapshot from OpenZeppelin. All this is implemented by OpenZeppelin library, and it uses the simple governance interface that we just read and address from OpenZeppelin. We have a constant of 2 days action delay in seconds. So I assume we have to wait 2 days between the time that we propose an action and we can execute it. And we have some state over here, the voting token, the action counter, and a mapping between integer to action called actions. In the deployment, we set a voting token, which is probably the DVT token, and the first action is going to be action number 1. Here we have the function queue_action that receives the target, value, and data. Anyone can call it. There is no modifier, but there is a check here, has enough votes of message sender. And if we don't pass this check, then we revert the transaction with not enough votes. So we need certain amount of votes in order to queue a new action. Let's take a look at this function. Has enough votes, gets the address who, gets the amount of vote, takes the total supply of the tokens, divided by 2, and make sure that the balance of the one who wants to create a new action is greater than half of the supply. And you can already see here that I left some audit comments, including audit issue that can say that there is a vulnerability in this function or a problem. The audit info tag says, check if the sender has more than half of the total supply of the voting token. And the issue say, this is a broken governance mechanism. Only if one actor controls more than 50% of the token supply, he can make proposals. So no one else can make proposals in this governance system, only if he possesses more than 50% of the supply. Also, it's possible to possess more than 50% of the token supply just by taking a flash loan from the pool with zero amount of fees and pass a proposal to drain the pool. Okay, so I already wrote here the solution, the vulnerability itself, because we can bypass this check by atomically taking a flash loan of a lot of tokens from the pool. It only needs to be 50% of the supply. So if we just take all the liquidity from the pool, 1.5 million tokens, it's going to be enough. Then we just pass this check and we can queue a new action. This action could be what we just decide because it's a target, value, and data. Let's see what action means. Here we have another check. The target is not address this. We cannot pass this contract address, so this contract cannot call itself. We also check that the data is greater than 0 and the target code is greater than 0. So we need to pass data and we need to call smart contracts. We cannot just call EOA accounts. And we set the action ID. The first one is going to be 1 and we write it into the state. We create a new governance action. We target, value, time, executed at 0 because we did not execute this action yet, and the data. And we increase the counter by 1 and emit an event. So here we just register an action in the contract, and I assume we can only execute it 2 days later. And we already understand that if we take a flash loan, we can pass this votes check and register a new action with whatever target value and data that we want. Then we have the execute action function that receives an action ID. So let's say we queued an action number 1. We can call this function with ID 1 and this action will be executed, but only if we pass this can be executed check. And this check essentially makes sure that 2 days passed between the time we queue this action to the time that we want to execute it. This is exactly what it does, and trust me, this code is legit and it's working and it doesn't have any flaws. I already audited it. Then we take the action from the state, we update the executed at, we emit an event, and we do function call with value, which essentially means we are doing a low level call to this data that we have in the action. So we essentially take the target of this action that was supplied by the user who proposed the action, and then we call this target, we call the function using the data, and using the value. So this contract, what it simply does, it allows someone who controls more than 50% of the supply to queue action, and action just means this contract calls another contract with certain data and value, and then 2 days later, we can call this execute function data to make sure this action is executed and this low-level call is made. So now that we have everything in mind and we also have an attack plan and a vulnerability plan, we're gonna take a flash loan. Then using this flash loan, we can queue action, then we can wait 2 days and we can execute it. And this action is just gonna be a call to this emergency exit function that is protected by the only governance modifier, because now we can call this function from the governance. It's an action. This governance contract is gonna make the call to the emergency exit function, and the receiver is going to be us. So we're going to get to have all the tokens from the pool. Time to take a look at the solution. So for this solution, I had to create a new smart contract because I need to receive a flash loan. I need to have this callback function defined. So I created here this Selfie attacker contract that is inheriting from I flash loan borrower because we need to implement the callback function. We have some state here: recovery address, pool governance token, action ID, and hash of the callback that we need to return to make sure that this pool will not break on us. In the constructor, I just set all the state variables, I passed them and I stored them in the state of the contract, the pool, governance token, and recovery. I just reorganized a bit the contract so it will look clearer. First, we have this start attack function that we're gonna trigger from our Foundry test. This start attack function is going to start attack by requesting a huge flash loan. We are trying to request a flash loan of 1.5 million DVD tokens. It's all the tokens that are in the pool, and we don't care about the data, so we just pass empty data. We request to receive all the tokens to our attacker contract. Now remember, after the tokens are transferred, this pool is going to call this onFlashLoan function, which is the function that we implemented right here, the callback function. We have some sanity checks that the sender is the pool and the initiator is us. We are the ones who requested the flash loan, and we delegated tokens to ourselves, to our malicious attacker contracts, so we can use this token later to vote and to create proposals. Then what do we do with all these tokens that we got? We create a new governance action, we queue a new governance action, and this action is very simple and straightforward. The target is the pool. We want to call from the governance to the pool. The value is ETH. We don't need any ETH value in this call, but the most important is the data. The data is the function that we want to trigger, and it's the emergency exit function together with the recovery address account. So we want to perform an emergency exit action and send all the funds to this recovery account. And we queue the action, we get the action ID, we save it in state so we can call it later with the execute so we know which action ID it is. And remember, we have to approve the tokens back to the pool with the fee. The fee is going to be 0, it doesn't matter. But once we did approve and return the callback success, the pool will be able to pull back the tokens to take them back, and this flash loan will succeed. So just using this liquidity in an atomic way for a millisecond, we were able to use this voting power and pass a malicious action. This is a classic flash loan and governance combined attack. By the way, if you're a bit lost and you're not sure about the solutions, you can always check my GitHub repository, Damn Vulnerable DeFi V4 Solutions by JohnnyTime. Feel free to start it, to fork it, to take a look at the solutions yourself. Everything is there. Okay, so now we're able to queue the action using the flash loan. Now we need to execute it. So we created another function. It's called execute proposal. That all it does, it calls the governance contract execute action with the action ID that we saved in the storage of the malicious contract. Now let's see how we deploy this contract and trigger the attack. We go back to the test Selfie. And first, I'm going to deploy the malicious contract with the pool, governance, token, and recovery. I'm going to call the start attack. Then I'm going to move the time forward 2 days. I'm using the vm.warp Foundry cheat code to take the current timestamp plus 2 days. So we are moving in time forward 2 days. And after these 2 days, I can just call execute proposal. And remember, this execute function is going to take the action that was queued. It's going to run it, which means it's going to call from the governance contract to the pool contract to the emergency exit function, and the receiver is going to be the recovery account. So the result of this is that the funds will be drained from the pool and go to the recovery account. And this should make this function pass because the balance of the pool should be 0 and the balance of the recovery account should be tokens in pool. Now we want to see if our POC works, so I'm gonna go and run forge test match path selfie, run the test, and let's see. And we did it. The test file passed, all the tests passed, and we were able to complete the 6th Damn Vulnerable DeFi challenge selfie completely with Foundry. If you enjoyed this video, make sure to like and subscribe to the channel for the next solution video and for more awesome Web3 security content. And if you have any questions, feel free to ask them in the comment section below. Thank you so much, and I will see you in the next one.